the backup or just have your own, let me know by raising your little blue hand. Alexis, is your hand up for that?
Yes.
Okay.
Is everybody getting the links that I post?
Yes, thank you.
Yes, thank you so much.
All right, I have Alexis,
Yeah,
I have Brianna.
they've been really helpful.
And Carmen, is that for recording? All right, so I allowed all those recordings. Good. Okay, so today we are going to finish chapter 7, and then we'll be done with this section. We'll have the review on Wednesday and the exam on Monday. Okay, so do you have any questions for me before? I'll do a little bit of a review of what we've done so far in chapter 7 before I move on. Any questions? Okay, then let's see. Brianna Chavez, can you please tell me the 4 components of respiration?
Is it pulmonary ventilation, pulmonary diffusion, transportation, and capillary diffusion?
That's exactly right. And which of those is considered internal respiration?
Internal would be capillary diffusion.
Good. Sydney, can you please tell me what is pulmonary ventilation?
Pulmonary ventilation is moving the air in and out of the lungs.
Okay, and what are the 2 terms we use for that?
Inspiration and expiration.
Good. London, can you please explain how inspiration works?
Sorry, I'm not too sure.
Okay, Caroline, can you please explain how inspiration works?
It's active and it uses ATP, right? And contraction occurs by the diaphragm.
Mm-hmm. Can you go into a little more detail?
Yeah. I have like little segments, but I know like air always moves down the pressure gradient. Contract diaphragm allows lungs to expand. That's all I pretty much have.
So there's a law we talked about with this. What is Boyle's law?
There's an inverse relationship between pressure and volume, I think.
Exactly. So can you relate that to inspiration?
So if there's an increase in volume, there's a decrease in pressure for inspiration, right?
Yes, increase in volume of what? Putting you on the spot here.
Oh, is it oxygen? No.
No, it's okay. So we're talking about when you're talking about volume here, we're talking about the amount of space that we have in your lungs. So it's not, the volume here is not referring to an amount of air or an amount of blood, it's referring to an amount of space. Okay, so as we contract the diaphragm, it flattens out, which allows the lungs to expand. When the lungs expand, that's an increase in the amount of space we have, which is an increase in volume, which causes a decrease in pressure based on Boyle's law. So then we have the pressure gradient, meaning there's a difference in pressure between the outside air and inside the lungs. We have higher pressure in the outside air, lower pressure inside the lungs, and the air will move down the pressure gradient from high pressure to low pressure, so the air will move into the lungs. It was active because we contracted the diaphragm. Okay, so expiration would then be passive. As you relax your diaphragm, it goes back up into its resting position, which compresses the lungs. When we compress the lungs, that's a decrease in volume, or decrease the amount of space you have, which drives the pressure up based on Boyle's law. Now we've created another pressure gradient, but this time we've got high pressure inside the lungs as compared to the outside air. So the air is going to move out as it moves down the pressure gradient. Make sense? So think about moving down the pressure gradient as moving from a crowded area to a less crowded area. Okay, the gases always want to equalize the pressure. They don't want to have a gradient. They want it to be equal. So think about if you're driving down Reseda Boulevard and you're coming up on a red light and there's 3 cars already stopped in one lane and no cars in the other. Are you going to get behind the 3 cars or are you going to go in the empty lane? Chances are you're going to go in the empty lane, right? Because we also like to equalize ourselves. We don't want to go somewhere where it's crowded. We want to spread out a little bit. Okay, so the gases behave the same way. They're going to move. If there's a difference in pressure, if there's a gradient, they're always going to move to try to equalize. So they're going to move from high pressure to low pressure so that the pressures can equalize. If pressures are equalized, there won't be any movement. Okay, unless there's a contraction that forces movement. Okay, then we talked about the lung volumes. We drew the graph. We identified and defined the different lung volumes. You guys have had some time to look over that since we last met. Do you have questions on those terms? Do you want me to redraw that and go over them again?
The graph on Canvas is really good. Thank you.
Yeah, that's a really good one for looking at the relationships between the different volumes.
Right.
Do you guys want me to spend time on that or no?
Yes, please.
How would you
On the test?
Yeah, how would you
Okay, so
do
you're
it on
not
the
going to
test?
be able to draw on the test. So you'll either be given a drawing and asked to label it, identify it, explain it, or you'll just be asked questions using the terminology. Okay, but there won't be a way for you to draw.
I have one real quick, simple question.
Mhm.
Does tidal volume have the acronym of TV, or
Yeah.
is that, it does, okay.
Okay, so I'm just going to draw these lines real quick here. It's not very accurate. It's not very accurate either. But you understand what it's supposed to be.
Yeah.
Okay. Okay, so this volume right here, Ismail, what would this one be?
That's your tidal volume,
Tidal volume, which is what?
which is the amount of air as you inhale. The first inhale, like a small, regular, normal inhale.
Mhm. Good. It's not just an inspiration though. It's an inspiration and an expiration.
Oh, okay,
So
okay.
it's the amount of air you move through your lungs during a normal breath.
Normal breath.
Inspiration and
Okay.
expiration. Yes.
Okay.
Good. Jasmine, what would this one be?
The inspiratory reserve volume.
So to me, that one is kind of common sense. The name of it describes what it is. It's your inspiratory reserve. It's the amount of air you could inspire beyond your normal inspiration. Okay, so when you're sitting in your chair just breathing normally, and then you take in a deep breath, that extra amount of air that you take in beyond what you normally take in is your reserve. It's your inspiratory reserve volume. Okay, so if we combine those two, Susanna, what would that be?
The inspiratory capacity.
Inspiratory capacity. So inspiratory capacity doesn't really have a word definition. It kind of just has a formula. So we'd say inspiratory capacity equals what?
Oh, TV plus the IRV.
Good. So inspiratory capacity is the combination of the tidal volume and the inspiratory reserve volume. Good. If we do this one, let's see. Rosie, what is this one?
It is the vital capacity.
Vital capacity. What's the definition of that?
Is it the formula?
You could give me a formula. This one has a formula and a word definition.
So the formula has vital capacity equals there was the IC plus the ERV.
Yes, that would work because ERV is this. Okay, so if we do that, let me do a different color. So I see inspiratory capacity is from here to here, and expiratory reserve is from here to here. So that would be vital capacity. That works. Can you put that into words?
Not too sure.
Okay, so this would be, if you look at what this curve means, remember this was a maximal inspiration and a maximal expiration. So this vital capacity is the maximum amount of air you can move through your lungs in one breath. Your maximal inspiration, your maximal expiration. Okay, Guillermo, what would this one be? I'm not hearing you. I see that you unmuted yourself, but I can't hear you.
I'm not talking yet.
Oh, okay.
I'm trying to look at my notes.
Okay.
I won't answer it. I'm gonna look at my notes. Can I come back to it?
Sure. Lizeth, what would this one be? Can you see where I'm pointing?
Isn't it residual volume?
Residual volume. Can you give me a definition for that?
The amount of air that cannot be exhaled from the lungs.
That's good. I'll take that. It's the amount of air that's left in the lungs after the maximal expiration, which means if it's stuck in there, you can't move that air. Good. And Esmeralda, what would those two together be?
Functional residual capacity.
Functional residual capacity would just be the combination of expiratory reserve and residual volume. Whoops. That should be. Good. There's one more missing. Effie, what's missing from here?
The total lung capacity.
Good. And what would that include?
It is VC plus RV.
Okay, so this entire thing plus the residual volume. Total lung capacity. Oops. So we could say that's vital capacity plus residual volume, but the vital capacity can also be broken down into the inspiratory capacity and the expiratory reserve volume. So there are several different ways you could write those equations. As long as it makes sense, then that should be fine. But so you need to understand the relationships between the volumes to figure out those equations. Okay, any questions on anything with the lung volumes?
Professor, I think you overdrew the FRC.
Oh, I did, you're right. Thank you. Thank you. That would be here. Was that Marcia?
Yes.
Thank you, Marcia. Okay, better. Other questions on the lung volumes? And I appreciate that, by the way, if I make a mistake. It doesn't bother me if you point it out. I prefer you point it out because it's going to confuse everybody if we leave it there. So I appreciate that very much. Okay, then we went into pulmonary diffusion, and we talked about the respiratory membrane. Svetlana, what are the four parts of the respiratory membrane?
The capillary wall, the capillary basement membrane, the alveolar wall, and the alveolar basement membrane.
Good. So let me just draw this up here again real quick. I'm going to add on to it. So this is the alveolar wall. This is the capillary wall. And then we have the alveolar basement membrane and the capillary basement membrane. Okay, so this is the alveola on this side, which is part of the lungs. This is the capillary on this side. Okay, do you want me to label those parts again, or are you guys okay with that drawing? Actually, I'm gonna go ahead and label it again so that you can have a complete picture. Alveolar wall. You guys can just go back to your drawing from last time. You don't have to redraw it. Capillary. Okay, and then we talked about breathing oxygen into your lungs. And so we have high levels, high levels of oxygen in your lungs from what you're breathing in as compared to low levels of oxygen in the blood, because this is deoxygenated blood that's coming from the exercising muscle. Okay, so here we have a pressure gradient. There's difference in pressure between the lungs and the blood. There's higher pressure of oxygen in the lungs than there is in the blood, and so the gas is going to diffuse across that membrane to go from the lungs into the blood. Right? And then for the carbon dioxide, we said there are high levels of carbon dioxide in this blood because it's coming from the exercising muscle, which is producing carbon dioxide. There's not a lot of carbon dioxide in the air we're breathing. So there's low levels of carbon dioxide here. So we have a pressure gradient. This time we have high pressure in the blood and low pressure in the lungs. That gas is going to move down the pressure gradient and diffuse across this way into the lungs. Okay, I believe that's where we stopped. Is that right?
Yes.
Okay, so we didn't do Dalton's law, right? We stopped here.
We did not.
Okay, so the air we breathe is made up of mostly nitrogen, oxygen, and carbon dioxide. We have a total air pressure. The amount of each of those gases is constant. Okay, so each gas contributes to the total air pressure. The more of the gas that's present, the more it contributes to the total air pressure. Okay, so each gas has its own partial pressure that it contributes to the total pressure. Okay, so this is Dalton's law. Let me do a different color. Dalton's law says that the total air pressure is equal to the sum of the partial pressures. Okay, total air pressure is equal to the sum of the partial pressure. So a partial pressure is the contribution of each individual gas to the total air pressure. Okay, so if 79% of the air that we're breathing is nitrogen, it's contributing a large amount of pressure to the total air pressure. Okay, 20% of the air we're breathing is oxygen, it's contributing less pressure to the total air pressure. So the more of a gas that's present, the more of its contribution to the total pressure. So if you have a high partial pressure of a gas, that means you have a lot of that gas present. If you have a low partial pressure of that gas, that means there's not a lot of that gas present. Okay, so the way we're going to be using that is when I say there's a lot of oxygen inside the alveola, instead of just saying there are high levels of oxygen, I will say there's a high PO2. If I say there's a high PO2, that means there's a high partial pressure of oxygen, which just means there's a lot of oxygen. Okay, it's contributing a lot to the total air pressure. Okay, so I'll just change this to say there's high PO2 in the alveola. There is a low PO2 in the capillary. So we have the gas gradient. So the gas will move down that pressure gradient from the alveola into the blood. So all I'm doing is adding that term of partial pressure. Okay, so the CO2 will become PCO2. There's low partial pressure of carbon dioxide in the lungs and high PCO2 in this capillary blood. So the gas will move down that pressure gradient from the capillary, from the blood into the lungs. Everybody okay with that terminology? High PO2 means there's a lot of oxygen. Low PO2 means there's not a lot of oxygen. Okay? Then I have another law for you. Stop me if you have a question. Henry's law says gas dissolves in liquid in proportion to its partial pressure. Gas dissolves in liquid in proportion to its partial pressure. Where do we have gas dissolving in liquid here?
In the capillary?
Yeah, so the oxygen, as it diffuses across the membrane, some of it's going to dissolve into the blood. Okay, so that's gas dissolving in liquid in proportion to its partial pressure. In proportion, again, means it moves together. If one is high, the other one will be high. If one is low, the other one will be low. So if partial pressure of oxygen is high, dissolving in the liquid will be high. If partial pressure of oxygen is low, the amount of oxygen that dissolves into liquid will be low. All that really means is that this is an efficient process. There's not going to be a lot of gases lost in this transition from the alveola to the blood. You're not losing a lot of oxygen. Most of the oxygen that comes in will be able to diffuse across and dissolve. Okay, that's really all that means. Stop me if you have a question. I have one more law for you, and this one's my favorite. Fick's law says, I'll tell you what it says first and then I'll explain it. The rate of diffusion is proportional to the surface area and the partial pressure. Fick's law says the rate of diffusion is proportional to the surface area and the partial pressure gas gradient. I'll give you a minute to write that down. Fick's law says the rate of diffusion is proportional to the surface area and the partial pressure gas gradient. Let's look at what that means. Rate means speed. Diffusion is referring to the movement of the gas across this respiratory membrane. I forgot to label the respiratory membrane. Okay, so the rate of diffusion is talking about how quickly the gas moves across the membrane. Okay, is proportional to, we already said moves with, okay, the surface area. So the surface area here is referring to the respiratory membrane. So if this is the alveola, and this is the capillary, the respiratory membrane is all of the space here where the capillary meets the alveola. That's where the gas exchange takes place. So if we have a capillary here, and a capillary here, and a capillary here, we have more surface area devoted to respiratory membrane. Okay, the more surface area we have devoted to respiratory membrane, the faster the gas can diffuse. It's proportional. Higher surface area means higher diffusion rate. Okay, you can kind of think about it as this respiratory membrane being a road, and the oxygen or the carbon dioxide is the car. So if we only have a little bit of surface area, it's like having a one-lane road. Only one car can pass at a time, so it's very slow going. If we have a 5-lane highway, more cars can go at once, so it's going to be faster diffusion. Okay, so the more surface area we have devoted to respiratory membrane, the faster the gas can diffuse. So the rate of diffusion is proportional to the surface area. Okay, we okay with that so far? Stop me if you have a question. The rate of diffusion is also proportional to the partial pressure gas gradient. Gas gradient is how big of a difference there is in the pressures. Gradient is a difference. So if there's a large difference in the amount of oxygen in the alveola and the amount of oxygen in the capillary, the gas will diffuse faster. If there's not much of a difference, there's not much of a gradient, the gas will diffuse more slowly. So you have to think about why there would be less of a gradient, why there might not be low levels of oxygen in this capillary, and that would be if you're not exercising. Okay, the amount of oxygen coming into your lungs is going to stay pretty much the same. It's going to stay pretty consistent. But the amount of oxygen that your muscles are consuming is going to change based on your exercise intensity. So if you're resting, your muscles don't need to consume a whole lot of oxygen. Okay, you might have a high capacity to consume oxygen in your quadriceps, but if you're sitting in a chair, they're not going to consume as much oxygen as they possibly can. Your muscles are only going to consume the oxygen that they need for whatever work they're doing. So if you're sitting in a chair, your quadriceps don't need to consume very much oxygen. So that oxygen will stay in the blood. Okay, so as this blood travels around your body and your body's resting, the oxygen is going to stay in the blood. So when it comes back to the lungs, after it's gone through your body, it comes back to the lungs, there's still a lot of oxygen in that blood. So there wouldn't be much of a gradient here. Okay, if there's not much of a gradient here, the gas doesn't need to diffuse. Okay, you don't need more oxygen in there. It's like if you go to the gas station, the gas tank at the gas station is always full. Okay, kind of like your lungs always have oxygen in them. If you go to the gas station and your gas tank is already full, you don't need to put gas in, right? But if you go to the gas station and your gas tank is empty, there's a larger gradient there, so you need to put gas in. So the gas is only going to diffuse if you need it, right? So if there's a big difference between the oxygen content in the two areas, the gas will diffuse faster. Okay, so Fick's law says the rate of diffusion is proportional to the surface area and the partial pressure gas gradient. So the more surface area we have devoted to respiratory membrane, the faster the gas will diffuse. The larger the gradient, the larger the partial pressure gas gradient, the faster the gas will diffuse. Okay, questions on any of those laws? I don't see any hands coming up. No questions? Okay. So then I'm going to move on to transportation. So we did pulmonary ventilation, inspiration, expiration, lung volumes, Boyle's law. We did pulmonary diffusion, which is the respiratory membrane, the gas diffusing across the respiratory membrane. We did Dalton's law, Henry's law, Fick's law. And now we're moving into transportation, which is now we have the oxygen in the blood on the hemoglobin, and we need to bring it to the exercising muscle. That's the transportation part. Okay, so I'm going to go back to the same drawing. Actually, no, I'm going to clear this drawing. So you can take a screenshot of this you want, because I'm about to clear it. 4, 3, 2, 1, I'm clearing it. Okay, so transportation. Most of the oxygen in your blood will be bound to hemoglobin. 98% of the oxygen in your blood is bound to hemoglobin, and the rest of it just dissolves in the blood. Okay, but most of it is bound to hemoglobin. So we have the term oxyhemoglobin to refer to hemoglobin that has oxygen bound to it. Okay, and then we have the term deoxyhemoglobin to refer to hemoglobin that does not have oxygen bound to it. Okay, so oxyhemoglobin is hemoglobin that is saturated with oxygen, has oxygen bound to it. Deoxyhemoglobin is hemoglobin that has already released its oxygen. It does not have oxygen bound to it. I don't use those terms a lot. I will more use the term saturation. So if your hemoglobin has high saturation, that means it's holding on to its oxygen. If your hemoglobin has low saturation, that means it's not holding on to its oxygen. Okay, so don't think about saturation being good and bad. It's not that high saturation is good and low saturation is bad, or the other way around. It kind of depends on where you are, where the hemoglobin is in the body, whether you want it to be saturated or not. So think about at the lungs. As the blood is going through the lungs, do we want that hemoglobin to be saturated or highly saturated or less saturated? What do you think?
Less saturated.
Less.
Why would we want it to be less saturated as it goes through the lungs?
I thought highly.
We want, as the blood goes through the lungs for the pulmonary diffusion, we want the oxygen diffusing from the lungs, the air that we breathe in, from the lungs into the blood attached to hemoglobin.
Right.
Okay, so we want the hemoglobin to be highly saturated as that blood is going through the lungs. When that hemoglobin gets to the exercising muscle, we want it to release the oxygen so it can go into the exercising muscle. So at the exercising muscle, we want hemoglobin saturation to be low. If hemoglobin holds on to the oxygen as it passes by the exercising muscle, we can't get the oxygen. We need the oxygen to go into the muscle and into the mitochondria. That's where we consume it, right? At the end of the electron transport chain. If hemoglobin never releases the oxygen, we can't get it into the mitochondria. Okay, so we need the oxygen to attach to the hemoglobin when it's at the lungs, and we need it to detach from the hemoglobin when it gets to the exercising muscle. Okay, so we need a system in place to trigger the hemoglobin to tell it when is the right place to release its oxygen. Okay, because otherwise hemoglobin has a strong affinity for oxygen. Hemoglobin wants to hold on to its oxygen. So as it's traveling around your body, it's going to hold on to the oxygen until something tells it to release. Okay, so now we need to go over the factors that affect hemoglobin saturation. Okay, this is how we're going to convince the hemoglobin to release its oxygen at the exercising muscle. So these are going to be factors affecting hemoglobin saturation. I'm going to put the abbreviation for hemoglobin here. I'm going to be using that, so make sure you know what that stands for and how to spell it. Okay, because you'll need to write it out on the test. So I'm going to go over 3 factors that affect hemoglobin saturation. First one is partial pressure of oxygen. Remember what that means. If PO2 is high, that means there's a lot of oxygen present. PO2 is low, means there's not a lot of oxygen present. So low partial pressure of oxygen will cause low hemoglobin saturation. A high PO2 will cause high hemoglobin saturation. Okay, so if we think about this, at the lungs, PO2 will be high. There's a lot of oxygen in the lungs. PO2 will be high Therefore, hemoglobin saturation will be high. That means hemoglobin is holding on to its oxygen. As that hemoglobin approaches the exercising muscle, PO2 is low at the exercising muscle, right? Because the exercising muscle is bringing the oxygen in, therefore the blood there is low in oxygen. So when the hemoglobin arrives at the exercising muscle where PO2 is low, it's going to release its oxygen. Saturation will decrease. Okay, let me say that again. PO2 is high at the lungs. When PO2 is high, hemoglobin will have a high affinity for oxygen. It will want to hold on to its oxygen and become saturated. When that hemoglobin arrives at the exercising muscle where PO2 is low, that will cause it to lose its affinity for oxygen, will cause the hemoglobin to release its oxygen, decreasing its saturation levels. That's what we want to happen. We need the hemoglobin to release its oxygen so it can go into the muscle and into the mitochondria so we can consume it. Okay, so there's a graph for this.
Can I ask you a real quick question?
Yes, of course.
On the low, you put HB with lowercase b, and on the high with the uppercase.
that
Does
was a
it matter? Does it make a
was
difference?
Yeah,
Okay.
that was just a typo. Effie, go ahead.
To clarify, you're saying that we want hemoglobin to be saturated at the lungs and unsaturated at the exercising muscle?
Exactly.
Okay.
Okay, so on the x-axis is the partial pressure of oxygen. On the y-axis is percent hemoglobin saturation. Okay, low, medium, high. I'm not going to write that here because it's a pain to do that, but on yours that you're writing, please write low, medium, high for each of these. Okay, then we'll draw a curve. So when PO2 is high, where would saturation be? High, medium, or low?
High.
High. So I'm going to put a point right there. When PO2 is high, saturation is high. When PO2 is low, saturation would be low. Okay, so this is not a linear relationship. Okay, I cannot just draw a line between these 2 points. It's a curvilinear relationship. Okay, and I'm going to start up at the high PO2 point and the high saturation point because that's at the lungs. So the high PO2, high saturation is happening at the lungs. The low PO2, low saturation is happening at the exercising muscle. Okay, so as we go from the lungs to the exercising muscle, there's a decrease in saturation levels. This curve means that the decrease is slow at first, and then there's a rapid drop off. Okay, it's a sigmoid curve. That's different from if you draw the curve like this, that would be incorrect because this means there's a rapid drop off at first and then it slows down, which is not right. Okay, there's a slow drop off at first and then it drops off quickly. Okay, so this is called the hemoglobin saturation curve. And we read it in this direction because we're going from the lungs where PO2 is high and saturation is high to the exercising muscle where PO2 is low and saturation is low. Okay, so when you're reading this curve, what it says is as PO2 decreases, hemoglobin saturation decreases. That's what this curve says. As PO2 decreases, hemoglobin saturation decreases. That's important because PO2 is low at the exercising muscle. So this means that hemoglobin will be dropping off its oxygen as it approaches the exercising muscle, which is exactly what we want to happen. Okay, questions on the hemoglobin saturation curve or how PO2 affects hemoglobin saturation?
CO2 is high at the lungs, and then it decreases as it's approaching the exercising muscle.
Mm-hmm. That's exactly right.
For the graph on both sides is low, medium, and high, correct?
Correct. Any other questions on this one? Okay, second factor affecting hemoglobin saturation is blood pH. Remember that pH reflects acidity. Higher acidity means lower pH. So low pH will cause, what do you think hemoglobin will do in low pH? High saturation or low saturation? I hear someone saying something, but I can't understand what it is.
High saturation?
Low pH will cause high saturation. Is that what we want to happen?
No.
Where would pH be low?
At the exercising muscle.
At the exercising muscle. What do we want hemoglobin to do when it gets there? Hold on to its oxygen or release?
Drop off oxygen.
We want it to release. So saturation should be low. Low pH will cause low hemoglobin saturation. Keep in mind, all of these things are helping us exercise. Okay, our body is not working against us. All of these functions that are occurring are helping us exercise. So these conditions at the exercising muscle are causing the hemoglobin to release its oxygen. Okay, so low pH will cause low hemoglobin saturation. So I'm going to draw a graph for that. The graph is going to start out the exact same way as the hemoglobin saturation curve. It's going to have partial pressure of oxygen on the x-axis, percent hemoglobin saturation on the y-axis. Okay, it's going to have the same low, medium, high, low, medium, high. It's going to have the same hemoglobin saturation curve here. It's not very good. Like that. Still not happy with that. It's very difficult to do on the computer. Something like that. Like that here. One more time. Yeah, that's not very good, but I'm going to leave it. Okay, so I'm going to label this one as normal pH. Then I'm going to draw another curve for low pH. So my question is, will the curve for low pH be above the normal pH curve or below it? What do you think?
Above.
Okay, so what would it mean if I drew the curve above it? What happens as you move up on this graph?
Saturation.
As you move up on the y-axis, what happens to saturation?
It's increased. It's high
It goes
saturation.
up. So will a low pH have a higher saturation or a lower saturation? Lower. A lower pH will have a lower saturation, so this curve needs to be lower, reflecting lower saturation. So this will be low pH. Okay, it's the same curve, it's just shifted. Okay, in 446, they'll refer to this as being shifted to the right. So a low pH causes the hemoglobin saturation curve to shift to the right. That means it's a decrease in hemoglobin saturation. Okay, so this curve is saying that a low pH will cause low hemoglobin saturation. That's important because pH is low at the exercising muscle. So this means that hemoglobin will be releasing its oxygen at the exercising muscle. Okay, I'm going to say all that again. This graph says that a low pH will cause a low hemoglobin saturation, or will decrease hemoglobin saturation. That's important because pH is low at the exercising muscle, so this will cause hemoglobin to release its oxygen at the exercising muscle. Okay, this graph is called the Bohr effect. The Bohr effect says that a low pH will cause low hemoglobin saturation. Okay, that's the Bohr effect. That's important because pH is low at the exercising muscle, which causes hemoglobin to drop off its oxygen at the exercising muscle, which is helpful. Okay, questions on the Bohr effect? You can either raise your little blue hand or just turn your mic on and jump in with a question. Okay, otherwise I'm going to number 3. Okay, third factor affecting hemoglobin saturation is temperature. Let's see. James, how do you think temperature will affect hemoglobin saturation?
It would go up.
What would go up? The temperature or the saturation? Or both?
Oh, the saturation.
Okay, saturation goes up when temperature goes
Up.
Okay, let's think about that. Would that help us exercise?
No.
What's going to happen to temperature at the exercising muscle?
It's gotta be high.
Right. Temperature is going to be high at the exercising muscle because heat is a byproduct of muscle contraction.
Yes.
Okay, so how do you think that will affect hemoglobin saturation?
Oh, it should be low. Should be the other way around.
Right, so high temperature will cause low saturation.
Yes.
Right, high temperature happens at the exercising muscle, which will cause hemoglobin to release its oxygen. Okay, all of this is going to help us. So just, you can figure out what's going to happen if you just think about what we want to happen.
Yes.
Okay, so I'm going to say high temperature will cause low hemoglobin saturation, which means hemoglobin is going to release its oxygen at the exercising muscle where the temperature is high. Okay, so we can draw this one. It's going to start out the same way. PO2 on the x-axis, percent hemoglobin saturation on the y-axis. Low, medium, high, low, medium, high. I'll start out with the same hemoglobin saturation curve here. Okay, and we'll call that normal temperature. Okay, and then I'm going to draw another curve for high temperature. Will the curve for high temperature be above or below the curve for normal temperature?
Below.
Below, because as we move down on the y-axis, saturation is lower. So higher temperature will cause lower saturation. So this is going to be high temperature. So just because it's higher temperature doesn't mean the curve is higher, because that high temperature has an inverse relationship with saturation. It's going to be lower saturation. Okay, this curve doesn't really have a name. You can just call this how temperature affects hemoglobin saturation. Something like Okay, so all of these three conditions are helping us release oxygen to the exercising muscle. So you need to be able to list and explain these factors affecting hemoglobin saturation and these curves. Okay, so you will not be able to draw on the test. So you might be given the curve and asked to explain it. So you need to explain what the curve says and also the importance of it. Those are two separate things. Okay, so for example, with the first curve that we drew, the hemoglobin saturation curve. The curve says that as PO2 decreases, hemoglobin saturation decreases. That's what the curve says. The importance of that is that PO2 is low at the exercising muscle. So this means that hemoglobin will be released into oxygen at the exercising muscle. Okay, so you need to be able to explain what the curve is saying and also the importance of it. Okay, questions on any of that? You should know which one is the Bohr effect. The Bohr effect only relates to the pH. The temperature is not the Bohr effect, the PO2 is not the Bohr effect, only the pH. We're good on that? Are you sure? That was a lot of information. Okay, then I'm going to move on to capillary diffusion. So we've now brought the oxygen to the exercising muscle and released it there. Okay, now we need to get it into the muscle and into the mitochondria. So let me go back to this drawing. I'm going to stay on this page and just add to it. So draw. If this is the muscle now, this is the capillary. This is the mitochondria. Okay, so the blood is moving in this direction. Okay, we have the hemoglobin here bound to the oxygen. Okay, it's coming from the lungs. So you have saturated hemoglobin coming from the lungs. If this muscle is exercising, tell me some conditions you'd expect to see here at the exercising muscle.
Low saturation.
Well, I'm not talking about the hemoglobin now. I'm talking about conditions that are created at the exercising muscle.
An increase in carbon dioxide.
Low in oxygen.
Let's see, hold on, let me see. High CO2, low CO2. What else?
High lactic acid.
Okay, what else?
High temperature.
Low pH.
One more.
Increase in hydrogen.
Okay, so these are the 6 local conditions at the exercising muscle that we described when we were talking about just controlled blood flow, right? These conditions sensed by the chemoreceptors triggers vasodilation, brings in more blood flow to the exercising muscle, right? Some of these conditions at the exercising muscle will have an effect on hemoglobin. Which ones?
Can you repeat the question?
Some of these local conditions created by the exercising muscle will have an effect on hemoglobin. Which ones?
Low pH, low
Temperature.
PO2. Right.
Okay, so there's a connection here. These are conditions that are created by the exercising muscle, which vasodilates the vessels, brings in more blood with more oxygen. As that hemoglobin approaches this exercising muscle, the temperature, the PO2, and the pH are going to have an effect on hemoglobin. What's hemoglobin going to do when it gets here?
Release.
It's going to drop off its oxygen right here. Okay, then the hemoglobin will be here. The hemoglobin will be here. Now it's deoxyhemoglobin. It has low saturation. It's released its oxygen. Okay, that's exactly what we wanted to happen. So these conditions at the exercising muscle convinced the hemoglobin to leave its oxygen behind. Okay, but it just left it right there. Where do we need the oxygen to go?
Mitochondria.
We need it to get to the mitochondria. How do we get the oxygen into the mitochondria?
Autoenzymes.
No, the enzymes are in the mitochondria. How do we get the oxygen to the mitochondria?
Oh, the myoglobin.
Myoglobin. Myoglobin's job is to transport the oxygen that's been dropped off, transport that oxygen to the mitochondria where we can consume it in the electron transport chain. Okay, so hemoglobin releasing the oxygen is not enough. Hemoglobin releases the oxygen, myoglobin has to pick it up and deliver it to the mitochondria, which means that myoglobin has to respond differently in these conditions. They're both operating in the same conditions of low PO2, high temperature, low pH. In those conditions, hemoglobin loses its affinity for oxygen. Hemoglobin no longer wants to be holding onto the oxygen. Myoglobin has to respond differently. Myoglobin still has to retain a high affinity for oxygen so that it can pick up the oxygen while hemoglobin's dropping it off. Okay, so hemoglobin and myoglobin respond differently in these conditions. So I'm going to draw this one. It's going to start out the same way. We're going to have PO2 on the x-axis. We're going to have percent saturation. This time it's not percent hemoglobin saturation. It's just percent saturation because I'm going to draw one curve for hemoglobin and one curve for myoglobin. Okay, so I'm going to start with the hemoglobin curve. This is low, medium, high, low, medium, high. Okay, so this is our regular hemoglobin saturation curve. I'm going to label this one hemoglobin. Okay, then I'm going to draw the myoglobin curve. So the myoglobin retains its saturation. Myoglobin stays highly saturated as long as it possibly can until the very last moment when it reaches the mitochondria, and then it will release. Okay, so the myoglobin curve is going to stay high. Saturation stays high until the very last, whoops, stays high until the very last moment when it drops off. Okay, so this is the myoglobin curve. So what's happening here is while hemoglobin is releasing its oxygen, myoglobin is picking it up, which is exactly what we want to happen if we go back to this drawing. Hemoglobin is here, releasing its oxygen at the exercising muscle. Myoglobin is going to pick it up so it can drop it off to the mitochondria. So as PO2 is decreasing, hemoglobin saturation is decreasing, but myoglobin saturation is not. Myoglobin saturation stays high. So while hemoglobin is releasing its oxygen, myoglobin is picking it up. That's important because it allows the myoglobin to deliver the oxygen to the mitochondria. Okay, as hemoglobin is releasing its oxygen in low PO2, myoglobin is picking it up. That's important because it allows myoglobin to deliver the oxygen to the mitochondria. Okay, if myoglobin didn't want oxygen in these conditions, we wouldn't be able to deliver it to the mitochondria. Okay, what you can't say is that myoglobin is delivering the oxygen to the exercising muscle. See how that's not right? But by the time myoglobin gets the oxygen, it's already at the exercising muscle, right? Myoglobin is inside the muscle. So by the time the myoglobin gets the oxygen, it's already inside the exercising muscle. So where is myoglobin trying to take the oxygen to?
Mitochondria.
Mitochondria. So mitochondria is not delivering oxygen to the exercising muscle. Hemoglobin is delivering oxygen to the exercising muscle. Myoglobin is delivering oxygen to the mitochondria in the exercising muscle. Okay, so we can call this one the myoglobin saturation curve. Except when we draw the myoglobin saturation curve, we draw it with the hemoglobin saturation curve so we can compare them. Okay, they're both on there. Okay, questions on that?
Yes, so myoglobin saturation stays the same until it receives the oxygen?
No, myoglobin saturation stays the same, stays high until it arrives at the mitochondria. The only time myoglobin will release its oxygen is when it gets to the mitochondria. Other questions on here? So you have four curves. You have the hemoglobin saturation curve, you have the Bohr effect, you have the how temperature affects hemoglobin saturation curve, and you have the myoglobin saturation curve. Okay, you need to be able to explain all of them, what they are and their importance.
I have a question.
Mm-hmm.
For the myoglobin saturation curve, you're showing that for the arrows, can you explain that?
This just means as hemoglobin's releasing the oxygen, myoglobin's picking it up. And all of these curves are in the book. So you might want to look through chapter 7 to get an additional explanation of all of these concepts. So this is all in the book. And in fact, if I were to give you an illustration of the curve, it would probably be the book's version of the curve and not my hand-drawn curve. So it might be a good idea for you to look at those.
So all the blue arrows mean is as hemoglobin is being dropped off, myoglobin is picking up.
As hemoglobin is releasing its oxygen, myoglobin is picking it up. So hemoglobin is unloading and myoglobin is loading.
It's like switching Ubers.
Yep.
You have capillary diffusion as for the last graph. Is that just another term, but the actual name is myoglobin? Yeah.
So capillary diffusion is the larger concept of the gas exchange of the muscle.
Okay.
So this is a detail of capillary diffusion.
Okay.
So the other ones were detail of transportation, how we get the oxygen delivered to the exercising muscle. This is how we get it into the mitochondria.
Okay, makes sense. Thank you.
Mm-hmm. Okay, so I have another term for you. Screenshot this if you want it, because I'm about to take it down. Okay, taking it down. So I'm going to draw this again with, this is the muscle. This is the capillary. So we have hemoglobin here bound to oxygen coming into the muscle. Okay, so let's say we have 20 milliliters of oxygen coming into the muscle in this arterial blood, In the venous blood coming out of the muscle, we have 15 milliliters of oxygen. How much oxygen did the muscle consume?
5.
5 milliliters. How did you figure that out?
20 minus 15, so 20 that was going in, and then 15 that was
Okay,
coming out.
so you did the oxygen content of the arterial blood minus the oxygen content of the venous blood. Tells us how much oxygen the muscle consumes, right? So that is called AVO2 difference. The A refers to the arterial blood. The V refers to the venous blood. So AVO2 difference is the difference between the oxygen content of arterial blood and the venous blood, and the oxygen content of the venous blood. Okay, AVO2 difference is the difference between the oxygen content in the arterial blood and the oxygen content in the venous blood. And it reflects oxygen consumption at the muscle. The more oxygen the muscle consumes, the larger the difference will be in the oxygen content in the two areas. Okay, so the oxygen content coming in, we look at it as staying the same, but there's only 5 milliliters coming out. How much oxygen did the muscle consume?
No.
15 milliliters. Okay, so AVO2 difference went up. There's a larger difference between the oxygen content of the arteries and the veins. So AVO2 difference went up, which means oxygen consumption in the muscle went up, right? Because the more oxygen the muscle extracts from the blood, the bigger the AVO2 difference will be. Okay, so as you increase exercise intensity, the muscle consumes more oxygen, AVO2 difference increases. Okay, the difference between the oxygen content in the arteries and the veins will increase as the muscle consumes more oxygen. Okay, this is a very, very, very important concept. After the midterm, we will talk about AVO2 difference a lot. When we talk about training adaptations, we'll talk about AVO2 difference a lot. So make sure you have a good understanding of this. Yes?
Repeat again, difference between O2 content in the arterial blood and the O2 content in what?
In the veins.
Thank you.
Mm-hmm. So this is arteries, this is veins. Okay, so the difference between the oxygen content in the arteries and the oxygen content in the veins is AVO2 difference. It's important when you write it that you have parentheses here, because if you write it without the parentheses, it looks like this, and VO2 written like this is oxygen consumption. Like we talk about VO2 max and VO2 peak, and that's not what we're talking about here. So make sure when you write it with the parentheses around the AVO2 difference. Okay, everybody okay with that term? A couple more terms for you. Hyperventilation. Breathing faster than is necessary, but this is not during exercise, not really during EPOC. Okay, EPOC we talk about taking in more oxygen than is necessary, but that's not really considered hyperventilation. Hyperventilation is more like at rest, if you're breathing too rapidly. And we mostly think about this commonly as like if someone's crying hysterically and they're hyperventilating, right? What are you supposed to do when someone's doing that? Do you know?
Make them breathe into a bag.
Breathe into a paper bag. Do you know why, Cindy?
Isn't it to control their CO2, like when they breathe it out?
Yes. So the problem with hyperventilation is that the person who's hyperventilating is blowing off too much carbon dioxide. So remember that carbon dioxide has a function. Carbon dioxide triggers the inspiratory centers in your brain that causes you to increase your breathing rate, right? It gives you the urge to inspire. So remember we talked about that with the bicarbonate buffer. And when you're exercising at a high intensity, you're producing a lot of lactic acid. Hydrogen gets picked up by the bicarbonate buffer. We produce the carbon dioxide. triggers your inspiratory centers. It causes you to breathe faster. So that's why you're always out of breath during high intensity exercise. Remember all that? That was a little while ago. So carbon dioxide has a function with our breathing. So if you blow off too much carbon dioxide, you no longer have that trigger that tells you to breathe. So you lose your urge to inspire. So a person who's hyperventilating will eventually pass out from not breathing, from not inspiring enough oxygen. Okay, so you put the paper bag over their mouth and it forces them to rebreathe the carbon dioxide that they're expiring, because there's not very much carbon dioxide in the air that we breathe. So you put the bag over the mouth, that forces them to rebreathe the carbon dioxide so that they continue breathing and they don't pass out. Okay, the reason this is relevant to exercise physiology is because we use it as a technique. We use hyperventilation as a technique in hydrostatic weighing, which we don't really use so much anymore. But have you guys heard of hydrostatic weighing? So hydrostatic weighing used to be the gold standard measurement for body composition. Okay, now we use bioelectrical impedance a little bit more because it's more practical. But we used to use hydrostatic weighing, which is underwater weighing. So in the lab, we used to have a huge water tank. And then, so you weigh yourself outside the water, and then you weigh yourself under the water because fat floats and muscle sinks. So if you weigh yourself out of the water and then you weigh yourself under the water, you can calculate what percentage of your weight is from fat and what percentage is not. So that used to be the gold standard measurement for body composition. But to do that, you can't take in a deep breath and then go underwater and sit on the scale, because the air in your lungs will cause you to float, which will be counted as fat. So you have to do a maximal expiration, get all the air out of your lungs, and then go underwater, which, by the way, is why the lung volumes are important, because we need to know what your residual volume is as part of this calculation. Anyway, so you have to do a maximal expiration. So imagine blowing out all of your air and then having to go underwater, completely underwater, and sit on a scale for an extended period of time, sit very still. It's uncomfortable. So the technique for that is actually to hyperventilate first. So you hyperventilate 8 or 10 times, blow off a bunch of carbon dioxide, then you do your maximal expiration, and then you go underwater, and you're comfortable underwater. You don't have the urge to come up for air. So you can relax under the water. It's a very interesting experience. So we use that hyperventilation because we understand the role of carbon dioxide and how that works. So we can take advantage of that. So we don't do that so much anymore. We don't have that tank in the lab anymore. So you guys don't get to experience that. But what you can do with that knowledge is this summer when you're swimming with your friends, you can bet them, say, I can stay underwater longer than you, and then turn around and hyperventilate a couple times and then go under. You win that bet. So you understand how carbon dioxide works. Don't hyperventilate too much because you don't want to pass out in the pool. So do this at your own risk. I'm not advocating it. I'm just saying if you understand the concept, then you understand how that works. Okay. Questions on hyperventilation?
So hyperventilation is breathing more than necessary?
Yeah, it's rapid breathing in excess of what is required. Yes. And the problem with it is it's dangerous because you blow off too much carbon dioxide, so you lose your I don't think of the word. You know what I mean. You lose the urge, you lose the trigger for you to breathe. So you end up passing out. But it can be helpful for things like hydrostatic weighing, used as a technique. Okay, another thing. Oh, am I out of time? Thank you, Svetlana. I just saw your message. Let me give you one more quick term, and then I'll be done. Thank you, Svetlana, for telling me that. One more term is Valsalva maneuver. Valsalva maneuver is holding your breath during exertion. So basically trying to exhale, you're contracting your expiratory muscles and trying to exhale, but you're blocking the air from coming out. Okay, so people tend to do this when they're lifting heavy weights or lifting something that's very heavy. So it's dangerous because when you perform the Valsalva maneuver, it spikes up your blood pressure in your thoracic cavity significantly, which can trigger a heart attack, especially for someone who has high blood pressure to begin with. Okay, this is why we tell people to expire during the, I'm losing my words right now. During the hardest part of the movement, during the effort, you want them to exhale. Okay, the reason we do that is because that's when they're most likely to hold their breath, and we don't want them to hold their breath. So we say exhale on exertion. That's what I'm trying to say. So we avoid the Valsalva maneuver because it's dangerous because it spikes up your blood pressure. But if you're working with a power lifter, competitive power lifter, powerlifters use the Valsalva maneuver on purpose as a bracing technique because it does add significant stability to your torso. So you can lift heavier weights if you hold your breath, but it's dangerous. So for the average person who's weightlifting, we try to get them to avoid the Valsalva maneuver because it's dangerous. But we all know that competitive athletes will sometimes do things that are dangerous in order to improve their performance. So Valsalva maneuver is one of those things. It is a bracing technique. If I were to be walking past you and just sucker punch you in the stomach, you would brace yourself. That's the Valsalva maneuver. That's what you're doing. It stabilizes your torso. So it is an actual stabilizing technique that works. It's just a very dangerous one.
Isn't it also bad for the pelvic floor, like to have that much pressure?
Yes, this is more in the thoracic cavity than,
oh, okay.
It doesn't affect your pelvic floor as much, but you can create pressure down there as well.
Can you repeat the definition for the Valsalva?
Valsalva maneuver, I just describe it as holding your breath during exertion. If you want a more formal definition, it's attempting to exhale with a closed glottis, which is basically the same thing. You're contracting your expiratory muscles, but blocking the air from coming out. Okay, so sorry for going a few minutes overtime. We are done with new information completely. Wednesday will be review. I'm still planning for it to be Jeopardy style, so I will not be reteaching everything. I will be asking you questions and you guys will be answering. Okay, so please come ready for that. Okay, your PLFs sent you a lot of messages over the weekend. Please read them, they're very important. They are putting together a lot of review sessions for you. So they're not just bothering you with useful information, they're sending out, here's some help, here's some help, here's some help, here's some help. So please read through those messages, take advantage of the help they're offering you. Nick has asked me to go over dyspnea. Dyspnea is another term on your terminology sheet. Dyspnea is shortness of breath, but it's not shortness of breath due to exercise. It's like abnormal shortness of breath, like if you were sitting in your chair and you were short of breath. Dyspnea. Okay, so feel free to stick around. I'll stick around for another minute or two if you want to ask me a question here, or you can email me with questions. Make appointments with your PLFs for one-on-ones, go to your workshops, go to the review sessions. I'll see you guys on Wednesday.
Thanks, Professor.
Professor, I have a question.
Go ahead.
So for capillary diffusion in the capillaries, does that make it deoxygenated or oxygenated blood?
So the blood coming into the muscle is oxygenated. The blood coming out of the muscle is deoxygenated because the muscle is extracting the oxygen.
Okay, so let's say for like in chapter 6, we were talking about arteries having blood that's oxygenated and veins being deoxygenated. Capillaries kind of fall into the artery category.
So let me see if I still have this drawing up. So yeah, technically, so this is the artery, this is the vein, and this is the capillary. So whether this is oxygenated or deoxygenated, it's kind of where the gas exchange is taking place. So you can't really say if it's oxygenated or deoxygenated. It's in between the two. So that's why I say the blood coming in is oxygenated, the blood coming out is deoxygenated.
All right. Thank you.
This question's from chapter 5. I was trying to find it in my notes, but I couldn't find it. I might have missed it or something. It's how many O2 molecules are consumed during oxidation of one carbohydrate molecule, and how many CO2 are produced?
Didn't teach it, won't ask it.
So, and then the following question is similar to, it's how many molecules of O2 are consumed during complete oxidation of a 14 carbon?
I didn't teach counting the molecules, but that was related to RER. The relationship between carbon dioxide production and oxygen consumption had to do with the RER. So make sure you understand the concept of RER, but you won't have to actually go in and count the molecules.
Okay, thank you.
Thank you for asking that, Esme.
Anything else?
I have a quick question. When you were talking about the capillary diffusion, that would be the muscle and how myoglobin will transport oxygen to the mitochondria, right?
Yes.
Okay.
Capillary diffusion is gas exchange with the muscle. Pulmonary diffusion is gas exchange in the lungs, but it's confusing because pulmonary diffusion also involves capillaries. Vanessa, I see that you're trying to talk, but I can't hear you. You're unmuted. You might just need to type in your question in the chat.
I have a quick question. What does FFM mean? I haven't written, I just have free mass.
Fat-free mass.
Fat.
Why is that on there? On some on the study guide?
It says name 3 requirements for the measure of basic metabolic rate. How do FFM?
Oh, okay. Okay, good question. So we talked about basal metabolic rate, the things that affect it when I gave you the ranges of numbers, what would make a person be at the higher end or lower end, and we talked about muscle mass. So fat-free mass is basically muscle mass. So the more muscle mass a person has, the higher the metabolic rate. All right, let me see your question. Can you go over the local conditions and why these conditions are happening? Sure. So at the exercising muscle, the muscle is consuming oxygen. So oxygen levels are low. PO2 is low because it's being consumed. CO2 levels are high because the exercising muscle is producing carbon dioxide as a byproduct of exercise, and also the bicarbonate buffer is producing carbon dioxide. So carbon dioxide levels are high. Hydrogen levels are high because lactic acid levels are high, because that's a byproduct of glycolysis, right? So the higher your intensity, the higher lactic acid, higher hydrogen, which also means lower pH. Those three are all related. And then higher temperature, because heat is also a byproduct of metabolism. So was that all 6? Did I miss one? So those are the conditions you'd expect to see at an exercising muscle, because that's what the muscle is producing. So now we talked about those conditions being sensed by the chemoreceptors, triggering vasodilation as part of blood flow distribution. And we also talked about those conditions affecting the hemoglobin, allowing for oxygen delivery.
Really quickly, that means that in order for vasodilation to occur, you need those local conditions at the exercising muscle.
Mm-hmm.
And then for vasoconstriction, it would be epinephrine causing it.
Mm-hmm.
Thank you.
This is specific to the exercising muscle. So we'll get vasodilation, like after you eat something, you'll get vasodilation to your digestive tract. That vasodilation is not being triggered by the same things. Okay, but we're not studying the digestive tract, we're studying exercising muscle. Anything else? You're welcome. All right, bye guys. I will see you on Wednesday.
Thank you.
Thank you.
Thank you.
You're welcome.